everyone. So since this is the last day of the workshop, I would like to first thank the organizers for inviting me and together this nice workshop. I hear anything like that? Okay. This talk is going to, the topic is going to deviate a little bit from the rest of the workshop, but hopefully you'll still find it interesting. So this is a topic my group have been working on. One of the topics my group have been working on for the last few years, which is measuring the expansion rate of the universe with standard gravitational wave standard Siren method. We all know that all these powerful cosmic probes in the last few decades, including CMB, Galaxy Survey, Type 1a supernova, all of these probes help us to shape the standard model for cosmology. Our observed universe appears to have very good agreement with what's described by this Lambda-CDM model. But is this model good enough? That is why we are asking if there is any unexplained experimental result. And this is one of the famous ones. So this tension in the Hubble constant's measurement between what's reported by the Type 1a supernova measurement from the Hsin team appear to be inconsistent with what's inferred from the CMB observation by the Planck team, assuming Lambda-CDM model. The tension between the two is as large as 5 sigma. There are also other measurements for this local universe expansion rate Hubble constant reported by different experiments that summarize in this plot. I know you cannot really read in details, but the idea, the message here is that the value lies all over the place. So does that indicate some unknown systematics, or do we need new theories to describe the universe? That has been the debate for the last decade. And this is where the gravitational wave observation can start to play a role. Because with this lovely compact binary, if we happen to measure their gravitational wave signals, and even better if we can capture the electromagnetic wave signal from these systems, then with this multi-messenger gravitational wave plus EMM multi-messenger approach, we will be able to measure the Hubble constant. And this measurement is going to be independent from the cosmic distance ladders. And that is why we might have some hope to say something about this big tension in H0. The plan for this talk is I'm going to first introduce the method, talk about the precision and accuracy of this measurement so that you can evaluate these measurements. Then we'll discuss some challenges and some future opportunities. Okay, so let's start with the Hubble slope. This is Hubble slope. And what it tells us is that in the local universe, we are able to measure redshift z, so the distance to an astrophysical object, and we can constrain the H0, the local universe expansion rate. Actually, for EMM observation, it is easier to measure the redshift, while distance is more difficult. The story reversed for the gravitational wave. For gravitational wave side, it's actually more straightforward to determine the distance to the source. So this is what standard Siren method is about. So let's say we have this binary. We're emitting gravitational signal received by, let's say, our ground-based gravitational detectors. Amplitude of this gravitational signals goes inversely as the distance to the source. If the source was further away, you would expect a smaller amplitude received by your detector. So from the amplitude of the signal, you can then decide what is the distance to this gravitational source. But certainly there are other physical parameters also affect your amplitude, and those are actually the properties that contribute to the uncertainty of our distance measurement. We'll come back to this later in the Let's say now we determine the distance from gravitational wave side. Comes the difficult part. We need to measure the redshift. Here's why that is difficult. Let's say now you have this gravitational wave signal, and it was only received by one of the LIGO detectors, LIGO Hanford side. Then the only way for us to tell which direction did this gravitational wave signal come from the sky is by our knowledge about our detector. We know that our detectors tend to be more sensitive to the direction above and below the detector plane. This is the L-shaped detector above and below. So you can say that, oh, then we think the signal is more likely to come from those directions. So that is marked by the yellow block there. Okay. Project it onto a flat Earth map, and it looks like two big blocks there, like that. Okay. But let's say now the signal was received by both of the LIGO detectors. Then we can start to compare the arrival time of this signal at our detector and better decide which direction did this signal come from. We can narrow the direction down to a banana-shaped light region on the right-hand side. Let's say now we have the European detector, the Virgo. Then typically European help us to throw away one of the bananas. So in the end, we end up with only one banana shape on the sky. The sky area for this one is on the order of magnitude of 10 to 100 of square degrees. And for those of you who are not familiar with this unit, just for comparison, the full moon occupies the sky at about 0.2 square. So you can imagine 10 to 100 square degrees is still very large on the sky. That would be very difficult for us to tell the astronomer to point their telescope and try to find out the gravitational wave source, measure their redshift. But the story totally changed if we not only capture the gravitational wave signal, but also their electromagnetic counterparts, electromagnetic emissions from the same system. Because traditional telescope, they typically do a much better job than what gravitational wave detectors can do. They can pinpoint the direction of the source on the sky very precisely. And this precise localization will then allow us to associate the source to their host galaxy. And from the measurement of the redshift of these hosts, we can decide the redshift of this gravitational wave source. With that redshift, and we combine it with the distance measured from gravitational wave side, we can constrain the Hubble constant. This approach also got the nickname of bright siren just because of the use of electric. With this approach, it was realized for the very first time with the binary neutron star merger detection, GDEC 170817. What you see is the banana shape for this out by the LIGO Virgo site. And after we put out this sky map, astronomers tried to scan through this red area, and that led to the discovery of what we call the kilonova emission. It's an optical near-infrared emission. And the big blob next to it was the host galaxy for this event. From the measurement of the redshift of this host galaxy, we determined the redshift, we combined it with the distance from the gravitational wave side, and we got this very first measurement of the Hubble constant with the standard siren method. What you see here is the posterior of this agent of measurement. Now, let me place back the tension we mentioned at the beginning. Obviously, we did not resolve any tension here. The good news is that we are currently observing, so we are in our the second half of our fourth observing run, which means more events are coming and we're getting more and more detections. So what you see here, this was what we did with single event. Suppose we have 5 events, then this is how well we can do. 10, 20. With 40 events, we will be able to achieve around 2.5% precision in the Hubble constant measurement. Then that starts to become an interesting precision. We can possibly say something about this tension. Okay, so now I know that asking from 1 event to 40 is a big ask. And that is why one of the questions my group have been trying to address is, can we try to reduce this number of events needed? Can we try to improve the precision of this measurement? And if you want to ask this question, then you need to ask, then what contributes most to the uncertainty of your measurement? Turns out it's because on the gravitational wave side, we are not able to measure the distance that well. And the reason we are not able to measure the distance very well has a lot to do with the degeneracy between the distance to the gravitational wave source and the viewing angle of this binary. Let me explain to you what is this degeneracy is about. We have our binary there. They are emitting gravitational wave signal. The emission of this gravitational wave signal is not isotropic. It tends to be stronger along the rotational axis of this binary, which means if you are lucky, you happen to observe the gravitational wave signal along their rotational axis. That's what we call a face-on orientation. Then if everything else is the same, you would expect this signal to be stronger comparing to what you observe from the side. That's what we call an edge-on orientation. However, we also mentioned that the standard Siren method, we are using this relation. The amplitude goes inversely as the distance. So you can imagine a scenario. If you have a face-on binary, but they are further away, you would almost receive an identical signal as an edge-on binary that's nearby. And without knowing which orientation you are observing this binary, you suffer from this degeneracy. You are not able to measure the distance very well. Now, there are several different approaches to improve this, to break this degeneracy. For example, we can try to use higher harmonic in the gravitational signal and get some extra constraint on the inclination angle, the viewing angle of this binary. But today I would like to talk more about this another possibility, which is making use of the beauty of multi-messenger observation. So, from the electromagnetic wave observation, the electromagnetic signal from these binary neutron star merger systems, we actually can try to extract some of the information of the viewing angle to this binary. What you see here in the cartoon that indicate 2 types of electromagnetic emissions we know about coming from this type of system, including the short gamma ray burst. They are very elongated jet, they're beam. So there's kilonova emission we mentioned. It is more isotropic, but it can also have some kind of structure and angular dependency. So from the interpretations of these electromagnetic signals you receive, you can get some information about the viewing angle of this binary, and that could help you to break the distant inclination angle or distant viewing angle degeneracy we just talked about. With this extra information, we are expecting a factor of about 5 to 10 fewer events needed to achieve the same kind of precision condition you are trying to achieve. That is a great improvement. However, when you hear this, one question you can immediately ask is, this EMM emission from the system is actually very complicated. Astrophysics is there, we don't understand the emission from these systems. So what is your interpretation of this EMM signal as bias? If you have a bias in your constraint on viewing angle, that's going to propagate to your distance measurement, and then all the way to your H0 measurement. That's going to bias your H0 measurement. This just shows you how severe this problem is. Let's say the H0 is actually the Planck value, the lower value. In principle, after around 10 events, it's what you should get. However, with only 10 degrees of bias on the viewing angle interpretation, we're just going to move to the Hughes value, and that is the last thing you want. Our major role here we are trying to play is to try to resolve the tension. You don't want systematic. But recently, the work led by my student, Alberto Samareset, we actually tried to combine different kind of information. We just mentioned that the viewing, there is this degeneracy of viewing angle, but actually from the gravitational wave side, although we are not able to measure the viewing angle of the binary very well, but we understand how the amplitude of the signal vary with different orientation of the binary. And from that, we can place some not very precise, very weak constraint, but some unbiased constraint on the orientation of the system. So what you can try to do is that you take that weak but unbiased measurement from the gravitational wave side, you compare it to what you get from the EMN side, which is very precise but could be biased. And after you do multiple of this comparison, you start to place constraint, you start to get some knowledge about how big this bias is, and then you can use that to correct for the bias. You can mitigate this bias, right? So since now we are talking about bias, you certainly can ask, all right, so that bias was mitigated. Do we have other sources of bias? Definitely. So here is a long list of possible systematic for the bright siren method. I group them depending on which part of the measurement they are affecting. For example, this very last one, part selection effect, that also has to do with our not enough understanding of the electromagnetic. There are physical properties that affect your electromagnetic emission when you are trying to do this analysis combining different events. You can suffer from unknown selection effect, and that could bias your result actually by a lot. But we recently also developed methods to mitigate this one. Coming back to this full list, although it looks like we do have a very long list of systematic, if we really look into individual of them, they either contribute to only a some percent level of bias, which means they are negligible currently, or we have already developed methods to mitigate them. And that is why it makes me feel more comfortable to say that maybe in a few years, with a standard siren measurement, we might be able to say something about this tension. So now, let me take one further step back. So for bright siren method to work, we require electromagnetic emissions. And that means likely we will need at least one neutron star in the binary so that they can generate light later. Then that means we'll need one neutron star mergers or neutron star black hole merger. And up to now, LIGO Virgo Cabra has only detected around a handful of this type of systems. Out of this around 5, only one has a successful electromagnetic counterpart association, the one I just mentioned, GF17 or 17. On the other hand, LIGO Virgo Cabra have detected more than 200 of binary black hole mergers. And astronomers did try to follow up these binary black holes merger detection as well. But up to now, there is no single electromagnetic counterpart that is widely accepted by the community that we think that is solidly associated with any of these binary black holes merger, which means the majority of them likely to be dark. But then is there any way we can try to turn this binary black holes merger into something useful for cosmology? Answer is yes, if you do it carefully. In the following, I'm going to introduce two possible approaches for us to make use of these binary black holes mergers for cosmology. So let me remind you what's great about this bright siren method we've been talking about is that the detection of electromagnetic counterpart help us to precisely decide the direction of the source on the sky. Without that, we are back to this banana. And within this banana, by the way, this banana is not a two-dimensional banana on the sky only. It's actually a three-dimensional banana because we have a distance constraint as well. So within this three-dimensional volume, there can be so many possible host galaxies for one gravitational amount. In principle, if you are able to measure the redshift of all of these galaxies inside, then you can statistically combine them. One of them should be the real host. And after you do it for multiple events, you can constrain cosmology. That is what we call a dark siren approach because there's no electron. There's so many problems with dark sirens. One problem is that, well, we probably just cannot get all the potential host galaxies inside this volume. The wrong assumption of which type of galaxies that is more likely to host an event, that introduces bias as well. And more fundamentally, for most of these binary black holes mergers, we don't localize them very well, which means that uncertainty volume is just too big. You've got too many possible galaxies inside, and your measurement becomes uninformative. Just to show you another real example, this is one of the real events we receive in our current observing run. That is banana shape. This is very typical sky map we receive. Sometimes we get two bananas, and sometimes we get the entire banana tree. This is just very typical events for sky map for our binary black holes mergers. But since now we are talking about hundreds of events, sometimes you can get lucky. Means the events can be fairly nearby, and for nearby events, we got high signal to noise, so it's a very strong signal. With this strong signal, we are able to localize them very well. Here is an example. I'll give you a second to look for where that uncertain area is. So this is one of the real events we receive in our current observing run. This is not the only example. I actually found several of them in our current observing run. They are all real. And with these events, I like to call them the golden dark siren, golden events, because for those very well localized events, now we are talking about a few orders of magnitude smaller in the three-dimensional uncertainty volume, which means you also have few orders of magnitude, fewer galaxies lying within this uncertainty volume. And that makes your measurement could start to become informative. Actually, just last week, we are using the Hubble-Eberly telescope at the McDonald Observatory in Texas to follow up one of these golden events. The data, we're still analyzing the data is still coming in. We also get some notification about some quality issues about our data because of a strike there or surface of a telescope apparently wrong here. Yeah, we got too many bugs in Texas. Yes, okay, so this is great. So this is one of the possibility for us to use binary black holes merger for cosmology. Another possibility is that we can try to see how cosmic expansion affect the, uh, the, the mass distribution of those compact objects we observe in gravitational wave detector. So we all know that the cosmic expansion leads to the progression of EMM wave after cosmic expansion. And same thing happened to the gravitational wave signal. So as after the gravitational wave signal propagates the universe due to cosmic expansions, they also shifted to a lower frequency. And that would make a system originally with certain mass m look like they were actually emitted from a heavier system rotating at at a lower frequency. So that means if you have some understanding of how what is a mass, it should be in the when the sources were emitted, when the gravitational sources were emitted, you could compare. You could, if let's say it looks like this, some source friend mass distribution look like that. And depending on what kind of cosmic expansion history it went through, you would end up with different type of observed mass distribution. So you can compare what you observe to what it should be originally in constraint cosmology. And because of this comparison, would highly depends on the peak and trough of this mass distribution. This method also gets a nickname of spectral siren because it is just like comparing those spectral lines in EMM. Okay? And recently, there are development trying to construct the mass distribution, so the astrophysical part, the mass distribution of the compact object, and the cosmological parameters all together to avoid any bias introduced by wrong astrophysical assumption, which start to make this method more and more unlikely to going to work. Okay, and because of this method, now it is not using any EMN counterpart observation. It doesn't require any measurement of the galaxy's redshift either. So it actually opened up the window for us to events at any redshift that is detectable in gravitational wave sensors for the future gravitational detector. We can observe those sources at very high redshift. And that might not be achievable by EMM observation. But we can start to place constraint cosmology at very high redshift with gravitational wave observation alone. So finally, let me give you a projection of how well we can measure these cosmological parameters, cosmic expansion rate, with our next generation ground-based gravitational wave detectors. Left-hand side is how well we can do with bright siren. Right-hand side is how well we can do with binary black holes merger, actual and the dark siren approach. But the message is we are talking about sub-percent level of precision on the constraint of cosmic expansion rate, so HOT, across different redshifts. Way to very high redshift with different type of standard siren measurement. And this measurement, again, I would like to emphasize is that it is independent from all the cosmic distance ladders. So in summary, in a few years, we'll be talking about percent level of precision on H0 measurement from the power observation. The further future, we'll be able to place some percent precision on the HOC across different redshifts, and that will provide us with a very stringent test of different cosmological.
for that talk. Do we have any questions?
Thank you for the nice talk. In the not this the previous slide, you were showing the error as a function of duration. So there is a critical point where it seems to shrink and then it's increasing again. What's the reason?
Yeah, this is a little bit complicated, but it also depends on like where those value black holes lie at, where they peak, where do we have most, because this is astrophysical reason. There's a peak of where you expect more merger to happen. That lies around one-ish. So that is roughly the corresponding.
Okay, thanks.
Thank you very much for the talk. So just out of curiosity, could you remind us of the number of event rates of neutron star mergers with the next generation detectors?
We will be talking about, let me try to, I want to get the number right. 10 to the fifth, maybe, per year.
Oh, okay.
Right,
It's
it's
quite
a
a
lot.
lot. Okay.
So what I remember is for SNR larger than 100, which is good, uh, about 500 per year, binary neutron stars.
Neutron star, but that is SNR of 100.
Larger than 100, which is maybe what you need for this kind of.
We can do 10, but it's just
Okay, so then it will be much larger.
Yeah. So yeah, 100 for Blau and 10, I'm sorry, maybe 10 to the fifth-ish for typical threshold.
So, is there an estimate for how much this banana will shrink once this detector in India goes online? And will you be able to do much better after that happens? Where you have better
I missed
localization?
the keyword. So you said with the LIGO India.
Presumably, you can localize these events much better in the sky.
Oh, yeah, so certainly the globe, that is why we want the global network. So certainly with India, LIGO India come online or Cabra getting more sensitive, they will all help. By factor, I wouldn't say order of magnitude, but factor of 3 is something you could expect.
Thanks.
So first, thanks for your interesting talk. But the H node is known that there's might be some scale dependence because of the CMB measurement and also the local universe. But in this in these measurements, can it solve the tension between the two, this like scale dependence? Because you just measure there's another measurements and standing like between these two tensions and tension is still there.
If I understand it correctly, so let me try to answer and see if that is what you're asking. So what we provide will be a direct measurement of the H naught. It is independent from other direct measurement of H naught. And then what you want to see is that whether our measurement consistent with other direct measurement, or it fall onto the other side.
Maybe I can just comment on that question because I think the question is already assuming that there is a new physics explanation for this tension. So if there was some real difference between early and late universe measurement, but that's at zero thought. I think the test here is to test lambda CDM, and so then there is a predicted value that should be inferred from these measurements. Okay.
Yeah, I was wondering about the spectral sirens method. You are assuming to know at a certain level the population as you know the mass distribution of the population. So that's also not very well known, right?
So originally I've been skeptical because of that. But I start to be convinced recently because they are development using non-parametric model, and they don't need to really assume a shape of how the mass distribution looks like, and then doing that and combining with cosmological inference, they are certainly you lose precision because of non-parametric. But unless that method has already been developed, that you are able to provide unbiased measurement with independent assumption.
Okay, I think in view of time, we should thank Hsin-Yu again for the very nice talk.